Hello everyone. My name is Katharina Lingelbach and I'm a PhD student at the University of Oldenburg and at the Fraunhofer Institute for Industrial Engineering in the field of applied neurocognitive psychology. I'm happy to present you today our research on machine learning approaches to recognize stress levels during a close to realistic driving scenario from electrodermal activity. We explored conventional supervised machine learning algorithms, automated machine learning, as well as deep learning. Why is driver state recognition relevant? Based on recent statistics, we know that approximately 1.3 million people die each year as a result of road traffic crashes. And distracted driving is identified as a major risk factor. The distraction can be elicited by external events outside the car, for instance, another driver to the side on the one hand, and on the other hand, by events in the car, for instance, a mobile phone, a conversation with another person, or the route planner of the car, among others. And by shifting the attention towards the distraction, the driver does not have enough resources to process relevant information to the driving task. And by monitoring the driver's mental states, safety-critical distractions, stress, or cognitive overload can be identified and potentially life-threatening situations and errors prevented. There are several methods to identify the driver states. On the one hand, you can use behavioral data like speed, reaction time, acceleration of the vehicle. You can use facial and body expressions, eye gaze behavior, neurophysiological signals, measuring the brain activity like electroencephalography or functional near-infrared spectroscopy. And last but not least, physiological signals like skin conductance, measuring electrodermal activity, temperature, or the activity of the heart. To infer the mental states from sensor data, signal processing techniques and machine learning is applied. There are different machine learning approaches which can be distinguished. First, conventional machine learning. In this approach, expert with domain knowledge extracts the features by hand. It's also called handcrafted feature extraction. And this can be time-consuming to identify the relevant data, information, and extract these features. And of course, there are also some limitations by the pre-choice of the expert. Extension of these conventional machine learning approaches are automated machine learning. This means that you feed the data into a model, into an algorithm, and this algorithm explores various selections and various combinations. And the combinations can be applied on the hyperparameter level, but also feature level, and the model selection itself too. Yeah, it's possible with and without automated feature selection. It is computational costly because you have to run a lot of combinations and explore them, and it needs a large amount of data. And the third approach is deep learning. Within a deep learning approach, feature selection can be done within the first layer of the model. It is also computationally costly and it needs a large amount of data. For EDA-based driver state recognition, deep learning is suggested to be particularly suited. In the research I present to you today, we were interested in which machine learning approach is suitable to robustly recognize driver stress states from EDA recordings within a close to realistic driving scenario. In the upper right, you can see the driving simulator and the sensor we used for the EDA recordings. A second research question was whether it is possible to robustly detect mental stress from rather short time intervals of 10 seconds. This is beneficial to react immediately on critical detected mental states of the driver. And to answer the research questions, we conducted a study with 9 participants and measured EDA, ECG, so heart rate activity, or heart activity, and behavioral responses in a close to realistic driving simulation. I here present only the electrodermal activity data and the machine learning on it. Let's have a look at the experimental design. Participants were asked to perform the driving task as a primary task with 3 different driving phases: manual driving, automated driving, and manual driving with rain as a difficult weather condition. In addition, we asked them to perform a secondary task, which was either an in-tray task, a visual cognitive task on a tablet, or an auditory N-back with a 1-back condition. And from these combinations of tasks, we defined the mental stress levels and therefore also the labels. So we had a low, medium, and high stress condition. In our signal processing pipeline, we first applied a low-pass filter to the data, then smoothed it with a moving average. We cut epochs of non-overlapping 10 seconds windows, and then we Z-score baseline corrected the epochs and did the decomposition into a phasic and tonic response. Afterwards, we explored 3 machine learning approaches for the driver state recognition. In 2 approaches, we extracted features by hand, which were statistical features from the tonic and phasic components, as well as additional peak-related features from the phasic response. And in the deep learning approach, we used a CNN, so convolutional neural network based deep residual network. And in for this deep learning approach, we didn't extract the further features, but fed the phasic and tonic signals directly into the model. And to compare the performance of the models, we did a Monte Carlo simulation and compared them with bootstrapped grand averages and confidence intervals. For the machine learning, we first did a train test split, then scaled the data with a standard scaler. We used a principal component analysis to reduce the dimensions and optimized hyperparameter within a cross-validated random grid search. And the performance was also evaluated within a 5-fold cross-validation, and we used the balance accuracy as a metric. For the models, we explored a linear regression, a linear discriminant analysis, a support vector machine, a k-nearest neighbor classifier, a random forest classifier, and a gradient boosting classifier. For the AutoML approach, we used tpot, which is a Python library for AutoML. And we decided for 100 generations, a population size of 500. We did a 5-fold cross-validation for the model selection. And it decided to choose 2 pipelines, suggested pipelines, for the later comparison with the conventional and deep machine learning. And also for the performance, we used the 5-fold cross-validation and balance accuracy. The pipeline of the 2nd generation we chose was a stacking estimator with a gradient boosting classifier and a random forest classifier. And the pipeline of the 100th generation was a stacking estimator with a Bernoulli naive Bayes classifier and a gradient boosting classifier. For the deep learning, we chose an architecture based on 2 already published articles on driver state recognition from physiological signals. The final model was a 1-dimensional convolutional neural network-based deep residual network. And as an input, we used the phasic and the tonic signals per epoch. And you can see in the model that in the middle we have got these 3 residual blocks. To compare the performance of the models, we first estimated an empirical chance level with a dummy classifier. The chance level was set at an average of 0.35 and a confidence interval of 0.1 and 0.6. You see the dummy classifier as the box at the very right of the figures. Then we did a Monte Carlo simulation and also bootstrapped the mean average of the models and confidence intervals. The confidence intervals are here indicated with the whiskers. And we have got the 5th and 95 confidence interval. And you can see that those confidence intervals which are not overlapping with the mean of the dummy classifier are significant. Also the model performance is then above chance level. And we have got above chance level performance for the conventional machine learning approach, for the support vector machine, k-nearest neighbor, random forest. And for the automated machine learning, we have for both chosen pipelines, so the second pipeline and the 100th generation pipeline above chance level. The deep learning model did not achieve chance level performance in the mental state recognition between low, medium, and high stress. As a take-home message, we could robustly recognize driver states, so stress states, from EDA recordings during a close to realistic driving, using handcrafted features with a conventional as well as an AutoML approach. And especially the k-nearest neighbor and support vector machine seem to be particularly suited. The deep learning approach was not superior. And probably this was due to the chosen architecture, the hyperparameters, or insufficient amount of data. And our third take-home message is that stacking and voting of classifiers might be beneficial for participant-wise classification. This is based on the suggestions of the AutoML approach. And for future research, there are some challenges to address, and one main challenge is the generalization among data sets, because we face the issue of small data sets, and therefore it is nice, or it would be beneficial, to combine data sets. And a second challenge is the generalization among participants. We did now within participant classification, but it would be also good to use a among subjects classification. And third, it is necessary to find time-efficient classification approaches, because for real-time state recognition, this is necessary in a naturalistic driving approach. And the implication of this research include the suitability of easy-to-use and unobtrusive sensors, and advantage of domain knowledge for feature extraction to identify the driver states in naturalistic driving scenarios. Thank you very much for your attention, and I'm happy to answer your questions now, and looking forward for a nice discussion.